All right, this is recording 2 of topic 4, variability and dispersion, okay? And we just left off with outliers. Now we're going to talk about the variance and standard deviation. Okay, when the mean is the appropriate measure of central tendency, that is, with a normal distribution, we can compute the variance and the standard deviation to describe its variability. So this is only for quantitative or continuous variables, that means interval ratio, right? Or scale and SPSS, that are normally distributed or fairly normally distributed. So the sample variance is just the average of the squared deviation of scores around the sample mean, okay? So right now we're going to look at something we're going to become familiar with. Right here, this is the sum of the squared deviations. So we talked about last week the deviation, which is a score minus the mean of the set, of the whole variable, right? So here you get the deviations, you square them because if you just add up the deviations, you get 0, right? So you have to square them and then you divide by n. So it is just the average of those squared deviations. This is the variance, okay? This part right here we'll be calling the sum of squares, the sum of the squares deviation. And we're going to use this throughout the course. So make sure you understand this as soon as possible. So larger variance means less consistency between scores, right? It means greater spread, right? Because it's how much deviation from the mean on average, right? So larger means greater spread. Now, if we take the square root of the variance, we get the sample standard deviation. This is more informative because it's an average deviation from the mean, right? So this is the average of the squared deviations of scores. This is the average deviation from the mean. We usually talk about it as a standard deviation. Oh, you can denote it S sub x or SD, standard deviation. In a normal distribution, a standard deviation is about 1/6 of the range, right? So again, sample variance, take the square root of that, and you get the standard deviation or the average deviation from the mean. Just think something standard, it's average. That should help, right? So let's look at that. So standard deviation in a normal distribution is about 1/6 of the spread. 68% of scores in a normal distribution will lie within 1 standard deviation of the mean, right? So here is -1 standard deviation, here's +1 standard deviation. So negative, positive, right? And 68% of the scores are going to lie right here within 1 standard deviation of the mean, either from 1 standard deviation below to 1 standard deviation above. Now, how spread out the distribution is doesn't really matter as long as it's normal, right? The differences here are not in that 68%. It's just the frequency, right? They're all together. This is just more frequency in a smaller range. So 68% of the scores here, here, and so forth, right? As long as it's a normal distribution. So a few rules with standard deviations: you can add or subtract a constant. It does not change the variability, but if you multiply or divide, it will. So just be careful with that. So far we've been talking about samples, but remember, we use samples to estimate population values. We use samples to make inferences about populations because we can't measure everybody in a population. So because sample statistics are generally biased, right? Because sampling error, and they usually underestimate population values, we have to correct for it. So here is the true or actual variance. Now, remember, we do not know in most cases, we do not know the true variance or true standard deviation of a population, but this is what it is in theory. We have sigma, remember that's Greek letter lowercase sigma, which is the population standard deviation, squared, which is the variance, right? And then over here, we have the standard deviation, which we just put the radical on, and it's the square root. So sigma is the population standard deviation, sigma squared is that population variance, right? However, we don't really know these numbers. So we have to estimate them based on sample variance and standard deviation. Okay, so to correct for this bias, right? So remember, sample statistics tend to underestimate the population variance. Okay, so they're smaller than they should be. To correct for that, we divide by n minus 1, which will make this whole value slightly bigger, right? So this is the estimated population variance, okay? This is the estimated population standard deviation. Again, we divide that variance by n minus 1, which is called the degrees of freedom rather than by n, okay? All right, so we are going to run through an example of this. Let me get a pen. Let me just use, so for some reason, the bar, this is X bar, this is just the mean of X here. It never shows up on these PowerPoints. It shows up on the smaller one, but not the big one. All right, so calculate the standard deviation. First, we have to find out what the sum of X is, right? Because we have to calculate the mean. Okay, so the mean is just the sum of X divided by N. So N is 1, 2, 3, 4, 5, 6, 7. Let me get a different color here. N is 7. Okay, the sum of X is 1 plus 3 is 4, 8, 10, 16, 21, 28, 28. So the mean of X is just 28 divided by 7, which equals 4. Okay, so now to calculate the deviation of each score, we just subtract 4 from it. So 1 minus 4 is negative 3. 3 minus 4, negative 1. 4 minus 4 is 0. 2 minus 4 is negative 2. 6 minus 4 is 2. 5 minus 4 is 1. And 7 minus 4 is 3, all right? Now, if we want to make sure we did it right, we just sum all these guys up, right? To see if it sums up to 0. So you can see negative 3, 3, that's 0, negative 1, 1, that's 0, negative 2, 2. So the sum is 0, right? Okay. Next, we have to square the deviations, right? So negative 3 squared, negative 3 squared equals negative 3 times negative 3. Remember, negative times negative is a positive, so 9. Negative 1 times negative 1 is 1. 0 times 0 is 0. Negative 2 times negative 2 is 4. 2 times 2 is 4. 1 times 1 is 1. And 3 times 3 is 9, okay? Then to calculate the sum of these squared deviations, we have to add them all up. So 9 plus 1 is 10, plus 4 is 14, plus 4 is 18, 19, 28. So almost never is the mean going to be the same as the sum of squares, but in this case it is, right? Okay, so next we want to calculate the sample variance. So this is just the sum of squares divided by n, which is right here. So 28 divided by 7 is 4, right? For the sample standard deviation, we have to take the square root of 4. So it's the square root of 4 equal 2. So how about the estimated population variance? This is 28 divided by n minus 1 is 6, right? So 28 divided by 6 equals 4.67. So 4 2/3. We have to round up to 2 decimal places always, unless otherwise instructed. To get the sample, the estimated population variance, we have to take the square root of that number. Oh, I messed up my calculator. 4.67, no. is 2.16. All right, so that's the full example of how to get the sample standard deviation and sample variance and the population standard deviation and population variance. Now, when we get to SPSS, SPSS will give you the estimated population values. So SPSS gives you the estimated population variance and estimated population standard deviation. If you need the sample standard deviation, as you will in chapter topic 5 or something, you have to calculate it. All right. Okay, so here's another example, which I suggest you do. All right, pause right now, do this example, and then come back and we'll show the answers. All right, so here is the answers, right? So the sum of x is 18, 3 plus 3 is 6, 7 plus 7 is 14, plus 4 is 18. The mean is 3, 18 divided by 6, because n equals, let's add that there actually, n is equal to 6, right? All right. So 3 minus 3 is 0. 3 minus 3 is 0 here. 1 minus 3 is negative 2. Remember, just in case you've forgotten, this is just 5 minus 3 because it's x minus the mean of x. This is the mean of x, right? 2 minus 3 is negative 1, and 4 minus 3 is 1. This adds up to 0 if you want to check your work. Then you just square these values to get the squared deviations, right? So 0 times 0 is 0. Negative 2 squared is 4. 2 squared is 4. Negative 1 squared is 1. 1 squared is 1. Then we add these up. So sigma deviation squared is equal to 10. Okay. Then we have to plug all these into these formula below. So let me get my pen out here. So right here, this is going to be 10 divided by 6. All right. Which is 1 1/3. That's the sample variance. To get the sample standard deviation, we have to take the square root of that value, which is 1.29. All right, to get the estimated population variance, we have to divide 10 times n minus 1, which is 5, equals 2, right? And to get the estimated population standard deviation, we have to take the square root of 2, which is about 1.41. All right. So your textbook is going to talk about computational formulas. We will not be using them. We use definitional formulas, which I find are more useful to help in understanding. After all, we can use statistical software to do all this anyway, right? So just a few symbols before we end. Capital S squared, that's a sample variance. S, sample standard deviation, or SD, describes variability of the sample. Okay, when you want to know, when you see a sub X or something, this just refers to the variable you're talking about. This could say sub Y, sub D, sub whatever, right? That just lets you know that it is the sample variance for variable X, okay? Sigma squared is the true population variance, which we don't know. Sigma is the true population standard deviation, which we also don't know, right? We make hypotheses about the true values. Lowercase s squared is the estimated population variance, and lowercase s is the estimated population standard deviation, all right? I remember n minus 1, which is the degrees of freedom, is in the denominators when we calculate the estimated population values. Okay, and here's a nice little table from your textbook or its sister textbook by Hyman if you want to use it. If you have any questions, please email me after posting first in the FAQ.